Hello again. I'm Dr. Marilyn Goski, and I'm a pediatric radiologist at Cincinnati Children's Hospital. And I'm very fortunate to be a member of the ACR Dose Index Registry. That is led by Dr. Rick Morin, Maitre Chatfield, and Laura Coombs. And I'm going to talk a little bit about the work that we're doing in pediatric CT related to the Dose Index Registry. Next slide. So what we're going to do is talk a little bit about image quality. We're going to try to discuss the role of image quality in determining technique and dose. We will also talk about diagnostic reference levels. What are they? And finally, we'll talk about dose index registries as a method to determine optimal pediatric CT, and a little bit about the results from the QuIRCC group. Next slide. So what is image quality? And this is actually a quote from Wikipedia because I liked it. And it says, image quality is a characteristic of an image that measures the perceived image degradation compared to an ideal or perfect image. So image quality is characteristic of an image that measures the perceived image degradation compared to the ideal or perfect image. And I thought that was a great definition. Next slide. But there's really a challenge with this, and this was discussed in an excellent article by Chet et al. And it says, and I quote, "In medical imaging, no single or widely applicable definition identifies the ideal or perfect image from either a subjective or an objective standpoint." Their article on this next slide goes on to say, "Nor is there a satisfactory method available to determine the amount of distortion or artifacts in the image." Next slide. So they conclude by saying that despite the central role that image quality plays as a criteria for successful dose reduction, a practical and quantitative definition has been elusive. Next slide. If you want more information about image quality related to radiation dose, there are many wonderful scientific articles and experts, particularly medical physicists, who could give you more information about this. One of the things I wanted to emphasize is that on this next slide, the idea that the old paradigm was referring to our CT scans as low-dose scans. We now have had a shift in this idea where the new term that we're talking about is optimization. And the reason that this new term has come into favor is that it not only takes into account dose, but it also takes into account the image quality. Obviously, if you lower the dose enough, the patient gets very little radiation, but you can't see the body. In this case, it's not going to help make a diagnosis that will help you and the referring physician take care of the patient. And I think on this next slide, it's emphasized in a recent editorial by Dr. Herb Kressel, who is the editor of the journal Radiology. And they go on to say that what is now a low-dose scan in the not-too-distant future will be the norm. And that with the amazing technologies that we have, particularly now with iterative reconstruction, that these changes are going to be incremental and the definition will change. And so they really suggest that we get rid of this term low dose, and I thought that was a great suggestion. So on this next slide, we're going to talk about the difference in CT compared to, let's say, routine radiography. And really the strength of CT is its ability to visualize structures of low contrast. And the task then is primarily limited by noise. And therefore noise is closely associated with radiation dose. The higher the radiation dose, the less apparent image noise. The lower the radiation dose, the higher the noise in the image. Next slide. And here's an example taken from an article by Dr. Goldman that demonstrates this concept of noise. And using a water phantom, you can see that on image A was performed at 270 MAS. The second image, with all other parameters being the same, the radiation that was used was 100 MAS in technique. And finally, this last image shows using a different filter, and you can see that this salt and pepper appearance is slightly sharper than before. So I think this slide really brings up the idea that noise is really part of the information that we need as one of the parameters in developing technique. Next slide. Now, this slide is not scientifically accurate, but I think that it is a pretty good analogy for this concept of noise and dose. And there's a website called PixelMonkey, and you can actually add or subtract the number of pixels that you want to create an image. And you can see that on this slide that as you have an increasing number of pixels, it's very easy to identify that this is the Mona Lisa. What's interesting is that if I were to poll this audience, many of you may look at image C and say, I can identify that that's the Mona Lisa. Others of you, group B, may say, gee, I can't say that. And a small group may say, I can't really identify abnormalities or the Mona Lisa until I have a lot more information and less noise or more pixels in this case. So it's that idea that how much noise you can tolerate also may be radiologist specific and also institution or facility specific. Next slide. This next slide demonstrates, I think, a wonderful early article that was written in 2002 by Dr. Manadeep Kalra. He is a leading investigator in radiation and dose. And what he did in adults was he performed a CT scan and then did a very limited number of repeat images at 50% of the radiation dose. And he stated that a reduction in CT dose is possible if the tube current is optimized for the patient's abdominal dimensions. And I think this was one of the first articles that really emphasized the idea that we could reduce technique for patients and still get diagnostic information. Another factor in relation to image quality is that it depends on the task and the size of the object that you're looking at. And if you look on this next slide, this is the American College of Radiology accreditation phantom. And as you can see, as some of the rods that are in this phantom get smaller, it becomes increasingly difficult to see this type of detail, thus showing that the amount of noise you have also impacts the amount of conspicuity of a particular lesion. And again, Dr. Kalra in that same article on this next slide shows that while you can lower MA, if you have lesions of different size, you may lower the MA so much that you're unable to easily and clearly define the abnormality. So the technique that you select is in part dependent on what it is you're looking for. Next slide. So what is the sweet spot? The sweet spot in baseball talks about where on the bat is the exact perfect place to hit the ball to get a home run. There the forces are completely balanced to hit that ball right out of the stadium. Next slide. And some other groundbreaking work that was done by Dr. Don Frush, who's going to be one of the speakers here at this symposium, is a technique that he investigated. That was some work also done by one of the CT manufacturers. And this was a wonderful project and insight because it allowed us to begin to get a handle on how much noise we could accept using computer simulation. And what you can see is in this picture that says true 40 MA and then a computer simulated 4 MA by adding noise, that he then was able to use this computer simulation and apply it for a baseline CT. So here are some images on this next slide from Dr. Frush. And if you see here, this is an image that was really obtained at 120 MA, and here you can clearly see this little tiny cyst. But as they brought the MA down to 100 or 80 or 60, you can see in this simulation that it is more difficult to see that tiny renal cyst. This same technique was used on this next slide in detecting renal stones in children. And what they wanted to try to do was find out how low they could go. And there are a series of images using a true MA of 250, and every one of the investigators was able to visualize this tiny renal stone. By the time they got down to the simulated 40 MA image, only one of the investigators was able to identify that stone. So I think that this shows that image quality is also determined by the clinical task, and we may be able to go lower in dose for specific tasks such as renal stone protocols. Next slide. So in summary, the optimal CT dose and technique is going to relate to the medical question to be answered, local preferences, and also the facility's equipment, which we did not talk about extensively. So let's go on this next slide and talk about subjective image quality as it relates to QuIRCC, or the Quality Improvement Registry in CT scans in children. Next slide. On this slide, you can see the homepage of the American College of Radiology National Radiology Data Registry. Here's a picture of the dose index registry here, and a small research group called QuIRCC. On this next slide, you can see the investigators. There's 6 institutions that are involved with this study. Next slide. So one of the questions that you may ask is, what is the typical radiation dose that you found used to perform a CT scan in the United States? Next slide. And I think that it is amazing to think about that we really don't know, click, what a typical radiation dose is in CT scanning in the United States. So a goal of our study was to develop what's called diagnostic reference levels for pediatric CT of the abdomen. One fact that this next slide underscores is the idea that in Europe there was a single body that was involved with monitoring radiation dose and actually having laws related to it. But in the United States, we haven't had a single agency that encompasses all of these aspects of radiation. So in spite of the fact that in 2010, for example, the FDA has placed increasing emphasis on this and created a new initiative, we have had various groups involved with radiation protection, and not one specific group that has overarching responsibility for this. So what is a diagnostic reference level? It relates to dose levels for exams for groups of standardized patients or phantoms. One of the things to understand on this next slide is that DRL are derived from surveys. They allow comparison to your peers, and the dose should be approximately 75th percentile compared to your peers for the same type of exam for a patient of the same size. And on the next slide, it tells us that DRLs should not be viewed as a dividing line between good or bad. Sometimes there's a reason why there's an increased radiation dose that's well justified. It's also inappropriate to use the DRL for regulatory or commercial purposes. DRL participating in these types of surveys are voluntary, and we know that that 75th percentile, that DRL, will change over time. So again, a diagnostic reference level on this next slide is your institution, your facility being at or below 75th percentile compared to your peers. On this next slide, we can see that Dr. Paul Shrimpton actually developed in the United Kingdom and for the European Union DRLs in 2000, 13 years ago. And he polled 40 scanners, this was a paper survey, from 7 different European countries, and at that time he used CTDIW as the dose estimate. They used 16 centimeter phantoms, patients of 3 ages, and actually were able to come up with some diagnostic reference levels. Next slide. So we also, when we're talking about diagnostic reference levels, we're talking about the upper target range, but what is the lower level for best practice in pediatric CT? And I think this next slide hopefully gives you an idea of what we're talking about. Here you can see that the hospitals that were involved with a hypothetical survey are showing a diagnostic reference level at the 75th percentile, and arbitrarily a 25th percentile was selected at the lower radiation dose. Here, a facility, before they do any intervention or quality improvement, you can see that their 75th percentile, or DRL, is higher than it should be. And then as they perform different investigations and quality improvement, this next slide shows how we want facilities to come into more similar alignment. For the QuIRCC study, we had a total of 960 scans that were contributed by different amounts by different facilities. On this next slide talks about our study design. It was all based on body width, and we used SSDE as our dose estimate, and we compared a subset of images from patients to evaluate subjective image quality as determined by our 6 site investigators, and we determined the SSDE for patients of the same body width in 5 different categories to calculate the upper and lower target ranges for each of these body widths. The image quality analysis we talk about on our next slide was performed on a subset of images and used as one factor to identify dose levels that were acceptable to the investigators and were used to determine a minimum and maximum target level using SSDE for each body width. And one of the things on this next slide that we found was that our 3rd percentile for a 5-year-old was 7.6 milligray, And this we use CTDIW. We converted it to what Dr. Shrimpton used. Quite a few years ago then, the 75th percentile was 12.5 milligray. So we can see that the radiation dose has dropped by 40%. We have more results that will be discussed in an article that's in press in Radiology that will give a very specific upper and lower target range. But we found that the QuIRCC DRLs were lower than the published international CTDI-vol and CTDI-W. We found, not unexpectedly, that CTDI-vol underestimated patient dose by a factor of 2 for all ages. We also found that patient body dimension is a better method than age to determine CT protocols, as we discussed earlier, and that we want to describe target levels for patients of different sizes using SSDE. So finally, I just wanted to emphasize that some of these questions that we've had as to what are target references, target levels for pediatric imaging, and how do my doses compare to other hospitals by doing investigations using SSDE and contributing to a dose index registry, we're really starting to learn. Thank you very much, and I look forward to talking to you with another discussion shortly.